Introductory Neuroscience and Neuroinstrumentation demo. This is a demo on the membrane length constant denoted as lambda. Okay. So welcome to a demo of the membrane length constant lambda. This demo is a complement to the lecture on axonology and neuronal biophysics. Right? So again, we are using metaneuron made by Professors Newman and Newman from the University of Minnesota. It's a free standalone program that can be used without restriction, and it works on Windows, Mac and Linux. If you're using Linux, you have to use Wine to get it going, and it's used to conduct neurophysiology experiments in silico. Okay. So as mentioned earlier, neuronal parameters, sodium potassium concentrations, equilibrium potentials and conductances can be easily modified. A virtual stimulator injects single or double current pulses into the neuron, and responses are displayed graphically and can be measured with the cursor, and families of traces can be generated and viewed in rotatable 3D plots. Okay. So this is similar conceptually to tau, but here we are looking at distance rather than time. So consider this image. This is a part of the demo. You inject the red trace indicates stimulus. You inject stimulus in the center of the dendrite or the axon. It doesn't matter, and then you see how it decays. Again, it's an exponential decay on both sides of the injected stimulus, and we can change different parameters and get an idea of how lambda is dependent on these parameters, like properties of the dendrite and axon, the stimulus intensity, and then you can look at potential versus distance or potential versus time, right? So just to remind you, the membrane length constant lambda, so passive conduction of responses through dendrites and axons is an important principle of cellular neurophysiology. Okay. So these principles were first formally enunciated by researchers such as Wilfred Roll, and if you want to model a neuron realistically, when I say realistically, I mean put in exactly all the physics of the dendrites, the dendritic tree, the axon, the cell body, etc. Then you need these concepts of the length constant lambda as well as tau. Many people don't bother, and they just use, and this is an older way of doing it, where you consider a neuron a single unit, and it's called a spike and integrate and spike. So you have many different impulses coming to the neuron. It integrates everything in a very, very primitive fashion, and it generates spikes. But when you use lambda and tau, you can get a realistic idea of how the neuron actually works, and this obviously is computationally much more intense and needs a lot of power compared to just the simple integrate and spike units. But this is realistic. Okay. So coming back from that digression, the length constant lambda, it shows the effect of the spread of voltage down a neuronal process, and again we're looking at the distance, not time. Time was for tau. So for simplicity, this process is assumed to be a dendrite, but it can also represent an axon. So the default parameters illustrate the steady state exponential decay of the membrane potential with distance, what you saw earlier. Okay. So you see a stimulus being put in here, and then the decay over a distance. And here the dendrite is depolarized for 50 milliseconds, and the membrane potential plotted at t equals 50 milliseconds. Lambda, or the length constant, is the distance where the membrane potential falls to 37%, 1 by eth of its value. And this demo models the dendrite as a cylindrical process of uniform diameter and infinite length, having a passive leak conductance. Membrane capacitance is kept at 1 microfarad per centimeter squared. So lambda depends on the membrane resistance. It also depends on the internal, that is the cytoplasmic resistivity. So you have the axon, the membrane, and you have the impulse going in here. The membrane resistance is the resistance of the membrane. The internal resistance is the resistance along the dendrite's longitudinal axis or the axon's longitudinal axis. And it also, of course, depends on the diameter. Diameter has an effect on lambda, which you'll see shortly. And the stimulus is applied to the dendrite as x equals 0. Okay? Again, this is distance. So a metaneuron simulates passive conduction by solving the cable equations. This was developed by Lord Kelvin in the 1850s because they were laying the cable between Europe, England, and the United States. And that is very similar to an axon. You have a cable. The cable has an outer conductor. It has insulation, and then you have a central conductor, which is pretty much how the axon also functions. So those equations were very useful and to model the cable properties of an axon or a dendrite. The third dimension, distance along the dendrite, can be viewed using the 3D graph option, and a range of distances is displayed by selecting the range function for position. Okay? So this is how it looks. So here you have the time, here you have the millivolts on the y-axis, and here you have the distance, how it decays. Okay? And this is a surface contour plot. So some of the exercises you can do is you can look at the steady state exponential decay of voltage with distance. So when it's depolarized, the axon on the dendrite at a particular point where x equals 0, this will decay with distance as it's passively conducted down the dendrite. So the other exercise to do is to vary the membrane resistance, then the internal resistivity, and the dendritic diameter. Then another exercise you can do is the passive conduction of a synaptic potential in dendrite. So we select the potential versus time and the synaptic potential stimulus rather than electric stimulus. And we set the stimulus width to 1 milliseconds. When you select a synaptic potential, it's a realistic scenario, because a square wave is not realistic. A synaptic potential is realistic. So then the time course of the synaptic potential can be viewed at different distances from the site of generation. Okay. So this is the metaneuron program, and here I have checked the membrane length constant demo, and just to briefly take you through the different boxes, etc. On the top left you have the dendrite or axon properties. So here you have the membrane resistance, kilo ohms centimeter squared. You have the internal resistivity, which is ohm centimeter, and you have the diameter. Here it's 0.1, and membrane this is in microns, and membrane capacitance is at 1 microfarad per centimeter squared. And here we have normalized the stimulus to the resistance in the diameter. Otherwise, you'll get graphs which will go out of the visual area. And the stimulus here is a square wave, which you see over here. It's in this little thingy in the red trace, and the membrane potential is maximum where the stimulus is given, and then decays exponentially on either side of the stimulus. And here we are looking at potential versus distance. Okay, and the time over here is 50 milliseconds, and the length is 500 microns, which is half a millimeter. Okay. So let us start changing things. Okay, so the membrane resistance. So again, the axon and the resistance, membrane resistance is the resistance of the membrane. So it's a so you're giving the stimulus here. It's a transverse leak outside and above and below the axon. And if you change the membrane resistance from 5 to 10, it becomes less. Okay, and if you change it to 100, it becomes even less. Okay, let's go back to default. So let's change the internal resistance. So let's change let's make it 1/10. So from 70, let's make it 7. Okay, again it goes for a longer period. And how do you make that out? Well, you can change the sweep duration over here, but before we do that, let's just go to the diameter too. So restoring back to everything back to normal, let's go to the diameter. So here it's 0.1 micron. Let's make it 1. So again, so it becomes, so you see, changing these parameters, makes the potential last for a much longer time. Okay, going back to default. So we can, instead of a square wave, actually let's do the square wave. Let's increase the amplitude. Okay, so we increase the amplitude from 2 to 10 times, 20. There you go. So again, it's huge now, but you have an exponential decay on either side of the point of application of stimulus, which is 0, and this is the stimulus. Okay, and we can make it back to normal. So we go to a synaptic potential, which is not a square wave, but which is more of what we get we encounter in the real state. So this is what it looks like, not that much different. So now we go back to square wave. So let's look at what happens when we change the distance, and we look at a range. Individual things are a little difficult, so we look at a range. So there you have a range of different stimuli, and you can see how it decays. Let's increase it a little more because I can barely see it, so I will make it 20. Okay. So it looks very nice and symmetrical, doesn't it? So what we do is we can do a 3D graph, and you can actually rotate it and get a sense. Here it's so much, and then you keep increasing it. You can see it being increased over there, and then it plateaus. Okay, it plateaus after a certain point, and after that it doesn't go above. And another way to look at it would be to look at a surface plot. Much prettier. But actually I can't see much on this. I prefer traces. Okay. All right. So let's stop that. Let's go back to defaults, and now let's look at potential versus time. Okay. And so let me change the sweep duration because I can't really see what's happening. So let's change it to 50. So you see the impulse, which is stimulating current over here, and you see the change in the membrane potential. Now let's change it to a synaptic potential. A synaptic potential is much much more gradual. Okay, and let's look at a range. Okay, again synaptic potential. Let's look at a range. Okay, and the sweep duration. Yeah, you can look at a 3D graph. You can see how. Okay. So you can see the position, where you're looking at the potential and looking at the time, and then you see the change in the membrane potential. Okay. Okay. So I would like to show one more thing. We'll restore everything back, and let's look at what happens when you change the diameter, because this is important. Because axons, dendrites, they all range. You can have dendrites. The squid axon is 1 millimeter. That's 1,000 microns. And you can have dendrites which are 0.1 microns. So it's different, how it behaves, how the current decays along the length of a dendrite or an axon in each of these instances. So here we are changing the diameter. Okay. And we have a range, begin value of diameter of 0.1 mu and ends at 100. I'm sorry, at 10. I would like to make it 100 and make this 1. Okay. Or in fact make this 10. Right. Yeah. So you have a 3D graph. It's better to have traces. Okay. So the first one, behaves normally, and then after that it overloads it. Okay. So these are not realistic. Okay. Though it gives you a sense of what's happening. You don't have such things happening. It's just to give you an idea of how the program works. Okay. and in fact, yeah. So as I was saying, here I've removed the normalizing part, so only the first stimulus works, and all the others are beyond the physiological limits of this program. Okay. So I come back to all to default, and then we can do the same thing for membrane resistance. So user range, and let's see, yeah, and now we are changing the membrane resistance. We have a begin value of 1 kilo ohm centimeter squared, end value of 20, and we increment it by 2, and we can see how it decays. We can do a 3D graph, and so this is the lowest, and then it keeps rising, okay, and then the decay, it's you can see the effect of the exponential decay, how it the lambda changes, and again we can use a surface plot if you like, and turn it around, look around. So here you see, over here you see the membrane potential, here you see the membrane resistance as it changes, and this is the position, and this is the decay. So similarly, we can look at the internal resistivity. Okay, so 1 minute. Yeah, so our beginning value is 70. So we can have a range. Okay, and we have a range of 10 to 250, and we increment it by 10, and we can plot a 3D graph and see the effect of diameter. Now again, as I said, suggested that it would be good if you keep this program running while you're going through the axonology and neuronal biophysics lecture, to get an idea of both the theory and the practical way of changing lambda, okay, and how it works, right? And we already went through diameter. Okay, so this is and also once you change these, you can also look at potential versus time and see how the change in membrane resistance, internal resistance, and diameter affects the potential in time. Okay, so that's basically it, and please play with this, play with all the different parameters, and if you have any questions, don't hesitate to contact us. Thank you very much.